of the sample means will be the same as the population mean. And what they mean by this is this. If I took, like I talked about this means, okay? If I took the whole population of the whole school year, and I said the average height of every classroom right now, okay? If I found the average height of every single person, okay? That's my mean, correct? That's my population mean of this school, okay? Now, if I went around and found out the mean of this class, and I found out the mean of this class, and all the way around and found each person's mean, right? Those are group means, correct? What this first sentence is saying is this. If I took the average of this class, and I took the average of Spilly's class, and I took the average of Boral's class, of Protsky's class, and all the way around, and found the average of those, found the mean of that, it's going to equal the population. Okay. So the means of the means will equal the population. That's what that's saying. Kind of weird, but it does work. The average is out. But the standard deviation of the sample means will be smaller than the standard deviation of the population, and will be equal to the population standard deviation divided by the square root of the sample size. So in other words, as we're taking these samples, all the means will be the same. But standard deviation, we're not going to be spread out anymore. Our groups are going to be small. You know, you can think about it. I mean, if you took sample means, it depends on what people are similar in different areas, right? You know, if you did these samples and you found the standard deviations, you know, if we did a standard deviation of a school, we're going to have people that range from really tall to really short, right? Now, if we get into each class and doing the standard deviation, this class is pretty even height, or standard deviation is going to be almost the same. Yeah, you go in maybe the basketball class where everybody's really tall, except Carson, everybody's really tall, but those people are going to still be above you in average, but their standard deviation is not going to be spread out. But put the two together, there will be differences. So that's what they mean by the standard deviation will be smaller as we move along. So what we do here, as we work on this formula, we change a whole bunch of stuff. It's called a correction factor, or standard error mean. As the sample size n increases, the shape of the distribution of the sample mean is taken with replacement for the population with mean of mu and standard deviation of sigma will approach a normal distribution. Mu is equal to mu. That's not a problem. But the problem comes in is our standard deviation. It's known as standard deviation of the means is going to equal our standard deviation divided by the square root of it. Okay? So what does that mean? So that means when I'm reading a problem, for example, this is the central limit theorem. Notice this. Z-squared. X bar minus the mean, or X minus the mean divided by standard deviation, right? You did that on your homework. Notice the problem changes. Now it's not X, it's X bar. It's mu. It says standard deviation of the means, but standard deviation of the mean is sigma divided by square root of that. Okay? Our formula changes. So when a problem looks like, I'm going to come up with a problem, this. A.C. Nilsson reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. You have 20 children between the ages of 2 and 5 are randomly selected. Find the probability that the mean of the number of hours they watch television will be greater than 26.3. What is the difference between this problem and the problems we were doing before? Sample population. The key word I think in here is right here. If you look back at a few problems we did in the previous section, it says find the probability that a person who receives this score, what percent of the score is that? 90 percentile. This score, one score, right? What does this one say? Find the probability that the mean, and that means the whole group. So now we're dealing with the whole group. Find the probability of the whole group. So what we have to do is we have to change it up. We have our sample size is 20.
our average of the mu of x, it's going to be 25, right? X bar is mean 25. And we've been looking at, not x bar, mu is 25. We're going to know 26.3. It's set the same way. We have on our z-score, correct? That's no different. So we're going to go to our z-score value here and say, okay, since we're calculating probability of a sample mean, find the probability of a sample mean, we need to use the central limit theorem. These two sections now, I'll tell you right now, are going to be tricky. These are not easy sections as you go into. Come on. Okay, so what we need to do is find our z, right? Z-score. Notice that we put in here, what our mean is. Our mean here is 26.3. From our original problem, you got the notes in front of you. Minus 25. 26.3 is what we're looking for, correct? 25 was our average. Divided by, and they say sigma x bar, which means standard deviation divided by the square root of n. 3 divided by the square root of n. That's the correction. This is the sampling error. Sampling error of our estimate. Sampling error of our estimate. Sampling error of our standard deviation. I'm saying it 3 times because I feel like a funny question on the test. Sampling error. Okay, just a little hint. So we work this out. 1.94. So now what we need to do is say, okay, that's our z-score here. That's right here. Now, if I think about it, this is my z-score. This is z-score 0. 1.94, right? The question says, what's the probability to be more than that? Correct? We have to take table E out. Take that chart out. You should have your chart.
I got a big.
You get your chart here. 1.94. I'm going to go on my chart. Go down to 1.94. What am I going to find? 0.4738. That represents this area right here. 0.4738. 1.94. Correct? I don't want that area. I want more than that. Right? So if I want more than that area, what I need to do is I say, okay, the whole half here is 0.5, so I'm going to take 0.5. This does it differently. I'm going to take 0.5 minus 0.4738, and I'm going to get 0.0262, which is, what is the probability that the average of that group is going to be over that? 2.6.
Questions on that one? The hardest part of these two problems is to decide which one. There's another formula. There's 3 different formulas. This one, central limit theorem, right? There's one we started with, x minus mu divided by standard deviation, right? And there's another one.
So, let's try another one. Here's another one. The average,
You notice they're really nice to you. I don't do this on test, but they're pretty nice to underline certain words. It's not going to happen on test. But they have
the average age of a vehicle registered in the United States is 8 years or 96 months. Assume the standard deviation is 16 months, and if a random sample of 36 vehicles is selected, find the probability that the mean of their age is between 90 and 100. Okay. First of all, we get the mean right in the middle here is 96, correct? We got 90 on this side. We got 100 over here, correct? So what we need to do now is say find the mean of their ages. The mean of their ages. So as the mean of their ages, what we need to do is find 2 z-scores actually. We're going to find 2 of them. So first z-score we're going to take is my mean, which is what? We're looking for 90 here, right? First one we're going to do 90, so we're going to say we want the mean to be 92. The average is 96. Divided by my standard deviation is 16 divided by the square root of n, which is square root of the number of samples, 36. Nice numbers. You're going to find that z-score. Then you're going to do the other point. So you got 100 minus 96. 16 divided by the square root of 36. I get this question a lot the last few days. There's someone that says doing this problem out and put the answer over there. Look at this, it's 90 minus 96 divided by this. I did something wrong. I did C squared. If it's on the left side of that zero line, zero being the middle, it's going to be a negative value. I don't know what you're going to get here. 4, 6, 2/3 times 6 is 18, 9. 6 divided by 4, 6 divided by 16 divided by 6 would be 3/8. Negative 2 point what? 25. Okay, and then this one on the bottom? Positive 1.5? So I got two numbers. You want to use your chart? Now you go on your chart, and you have to look up 2.25. Well, 2.25 is 4878. Okay, sounds good. So this area right here, there's a negative 2.75 right here. This area here is 0.4878. And this area right here, 0.4332. I'll agree with you. So the area, if you want between 90 and 100, we're going to take those two areas and add them together, and we're going to get whatever it is, I don't know. 92 what? That's it? So 92.1% chance that the sample means are going to be between. Okay? No. I can't work the only way sample. Okay? Is it? But knowing which formula to use. I'm going to come back to that one. We just did a couple of these now. We're going to go back to the other option. Sampling. Okay, now the formula. Finite population correction factor. Another formula. Two more to go. The formula for standard error of the mean is active when samples are drawn with replacement. Okay? Or are drawn without replacement from a very large or infinite population. A correction factor is necessary for computing the standard error mean for samples drawn without replacement from a finite population. Okay, what's it? The last problem we had was with replacement. We put the value back in. Drawn out with it. This is drawn without replacement. Or from a finite population. That means nothing, know the population, right? So this is going to be, before it was a sampling error, right? Now we're going to do with the correction factor. It's a correction factor for the standard deviation. We corrected it a little bit before, right? When we dealt with means, we corrected this standard deviation. Now we're going to correct it some more. Because now if we're not replacing it, we have to throw some more correction. So the correction gets to be really fun. We're going to add that to our formula. We're going to add this to our formula. The correction factor is computed using the following formula. The square root of n minus n over n minus 1. Where n is the population size and n is the sample size. So we know our population, how much our population is. Okay? And n small n is sample. Another way I look at this a little bit is this. If you notice the previous samples, it didn't tell us what the population size. It just said the sample size of this. Correct? Usually if it starts getting into population size and a sample size, we're going to have this correction. Okay? And the replacement is not key. The standard error of the mean must be multiplied by the correction factor to adjust for the large samples taken from a small population. So, in other words, change pages, let's go. Our z-score, I'll put it right here. Cool. Our z-score, the standard error for mean, must be adjusted when calculating the formula for z-value. So our z-value is going to be x bar minus the mean. Now it's divided by the sigma divided by the square root of n times the square root of n minus n over n minus 1. We're going to correct this one. So we got three different formulas.
When did you use each
Now, let's look at the next problem and talk about it. Oh, I didn't even give you a problem like this. I didn't even practice that. Whoa. My board's jumping everywhere. So, if we look at, let's see if I can find one real quick before we go to the next part here.
Hopefully there is one in here. We'll check around 6, 7, 6. Look on page 331, number 20. If you look at 320, 26 here, it says, in a study of life expectancy, everybody there? You there? Okay. It says, in a study of life expectancy of 500 people, so there's our big N, big size, right? In a certain geographic region, the mean age of death was 72 years. So mu is 72. And the standard deviation was 5.3. Standard deviation 5.3, right? If a sample of 50 people, little n, from the region is selected, find the probability that the mean life expectancy will be less than 7 years. X bar is 7. You see the difference in the question? We have a finite population. We're drawing a sample from that population. We're not replacing it. Now we have this other correction factor. Okay? So if I was doing this problem, what you might have to help me with the numbers. I would have to, if my pen starts working here. Okay? Maybe not. If I was writing this out, I'm going to have a z-score of, on top, I want to do x bar, which was 70, correct? I'm going to get my z-score first. 70 minus 72, that's the easy part, divided by, okay, hang on 1 second. That's 72. 72, and then it's 70 is 5.3. Square root of 50 times the square root of capital N, which is 500, right? Minus small n, which is divided by capital N, which is 500 minus 1. That makes sense. In the formula.
Oh, it's in the formula.
It's in the formula. So if I work this whole thing out, I'm going to grab a calculator here. It's not a grab it. So I got 5.3 divided by, I'm just going to do the bottom up here, square root of 50. Got that answered. And then I'm going to take the square root of a fraction, and I have 500 minus 50, 500 minus 1. And then I'm going to multiply those two together. And then I'm going to take the negative 2 on top times that answer. If I worked everything out, I ended up with a z value of, and I don't know why my pen is doing this right now also. I did not get a z value back. I had a z value, maybe I did it wrong, but I have a z value of a negative 1.42.
I got a negative 2.
I'll look again. I took the bottom here, 5.3 to.
Majority moves. That's what you mean, Tiffany.
I did 53 divided by square root of 59.
Okay, let's see this again. It was 5.3 divided by the square root of 50, right? I found that. Then it was the square root of 500 minus 50 over the square root of 500 minus 1, right? And I calculated the square root of that, right? Then I took those two numbers on the bottom and multiplied together. Then on top you get a negative 2, right? Oh, I'm wrong. I guess I don't know if negative 2 times that. It should be negative 2 divided by that, right? So I end up with negative 2.8095.
Yep.
Negative 2.80985. So I'm going to use a negative 2.81. I have no clue what's going on.
Maybe you have to count
It was working up to this hour, so I don't know what's going on.
them.
So find that in your table. Draw me a picture, the graph. Find me the picture there. Well, what was the question asked? Look back at the question.
Less than
So now, let's see if it works a little bit better now. Okay. So what we have so far is this. You're going to have a graph, and it's a negative 2.82, right? So you're looking right here, negative 2.81, I think it was, right? We're looking for less than that. So we're looking for that area, correct? So you went on your charts and found this area. Then you found the chart.
4975.
47.975. And to find this area, then we're going to have to take 0.5 minus that area, 0.4975. 0025. So 0.25. So very small percent, 0.25%. The chance that value is going to be less than 7. When we start working with groups and means, the percentages are going to get very small. Because you're not saying, well, what's the chance of one item being here? You're saying, what's the chance of this whole group happening to be the average from here? So the chances are getting very small. Does that make sense? So that's the 3 types of problems to deal with that. Now, let's see if we can get anything working here. Next slide. Normal approximation. A normal distribution is often used to solve problems that involve binomial. When n is large, say 100, the calculation is too difficult to do by hand using a binomial distribution. So he said normal distribution often used. Okay, so we're going to do another type of test. Remember binomial from last chapter? That's why it's nice to have these 2 chapters together a little bit, because binomial last chapter dealt with the yes or no question. You either get this or you... No, there's 2 options, right? So we're going to do a binomial distribution here. Now, what do we have to do? We have to make sure it's a binomial distribution. We're going to do this. Binomial distribution, the normal approximation to a binomial.
you have to take the number of sample size times p, probability of success, p is the probability of success, and it has to be greater than or equal to 5. And the number of sample size times q, q is the probability of failure, and that has to be greater than or equal to 5. Now, if it's not equal to greater than or equal to 5, then you can't do it. It has to meet those stipulations. In addition, the correction for continuity may be used in the normal approximation to binomial, and that correction means that any specific value of x says 8, the boundaries of x. Now, we're going to talk about this boundaries, how it works. We have to have a little correction factor when we do a binomial. It's not precise. That's what happens with statistics. It says, well, if it's this kind of test, we're not going to be really precise here, so we have to have a little correction factor to make sure we're within our range. Like the last two sets of problems we did. We can have the correction factor because we were in this range. We need to make sure we're in that range. We have a little correction. So as we look through here, we have some corrections. Now I'm going to jump to this. What is the correction factor? Couple things. I'm going to draw it over here. I don't think I can get my board to draw. The correction factor means this. If I have a value on the normal distribution, well, let's say I want to find the z-score of, I'm going to make it easy, 1. Okay? With a binomial, we're not going to just go on our chart and say, okay, let's look up 1. Okay? What we're going to do is we're going to look up half a unit on both sides of it. So if we're looking for 1, we're going to look, if it's equal to 1, we're going to look a little bit on this side, and a little bit on this side. So we're going to look from 0.95 to 1.05. Okay? Why? Because what happens to all those values? If we had a one of those values and round it down, it'd be rounding down to majority have 1, right? Or between those two values. So we're going to look at those correction factors as we go through. The hardest part on these types of problems is the part of determining what's going to do. If it's greater than, so if it's less than this value, it's 100. Notice here, if it's greater than a, okay, let's say for example, if I want this value to be greater than 1, that says we use what? Greater than 1, we're just going to take and add on 0.5. So in other words, greater than. So if we wanted to find our z-score, it's going to be greater than 1. Okay? We're going to work with a z-score of 1.5. And we're going to work with different values of that. Okay? This is our x value, actually. Now it's z value, x value. Okay? Now, what happens here? What happens if we add a little bit? Let's say we add greater than or equal to. Now we go to the other side. Now we're going to say 0.5 in the bottom. Okay? We're going to add certain values more. So this is a really tricky part. I'm going to show you an example. Let's say from here. And it's easiest to show an example than trying to explain this as you go through. Let's start with this problem right here. A magazine reporter I'm going to go back a couple slides first. Hang on. We know how to find mean and standard deviation, so we're good to go. Okay. So the first one, the magazine reporter, that 6% of American drivers read the newspaper while driving. Did you? So 6%. If 300 drivers are selected at random, find the probability that exactly 25 say they read the newspaper while driving. Okay. So they wrote us some information. First of all, probability of success. Probability they're going to read the paper is 6%, correct? It's probability of failure, 94%. That's pretty easy. And our sample size is 300, right? So the first thing we're going to do on this problem is check to see if it's a normal approximation. And what I mean by that is this. N times P. 300 times probability of success.
300 times 0.06 is 18. Is it greater than or equal to 5? Yes. Other one, n times q.
Marlene, will you please come to the office, Marlene?
N times q. 300 times 0.94? 202. Way better than 5, right? So it's approximately normal. If it's less than 5, we can't do the problem. Now, if you remember from last chapter, and remember this test coming up is chapter 5 and 6. If you remember from last chapter, how do you find mean of a binomial distribution? You take n times p. N times p. So we already know our mean is 18, correct? And we know our standard deviation on here is the square root of n times p times q. So our standard deviation here is 4.11. Those are from last chapter. Do I remember this? Maybe? Probably not. We'll see. Okay, we got that so far. Now, when we go to the next step, it gets to be write the probability. We want the probability x to be equal to 25, correct?
X to be equal to 25. So, let's see if this works. What we're looking here is this. We're looking for the probability, okay, equals, if you look back in the previous pages, equals 25 means we're going to add half and subtract half. So really we're looking for the probability that x is greater than or equal to 20, here we go again. 24.5 what? Nothing's working right now. So.
Well, it's x is greater than or equal to 24.5. And I'm just going to move it down. I think you can see it here. And my pen's not syncing very well. So I'm just going to go this way. We're going to look for between. Now I cloned it instead of copied. There we go. Cut. We're looking for between 24.5 and 25.5, right? We added 0.5 and we subtracted 0.5. So how many z-scores do we have to find? We're finding 2 z-scores. We have to find both z-scores and find out the area between those 2 points. So as we look ahead, we're taking both z-scores. We're going to take 24.5 minus 18, which is our mean, divided by 4.11. What's nice about this rule is we do not have to use any correction factors or sampling errors. We just use the regular z-score formula. And we get 2 z-scores. We're looking for a z-score between 1.58 and 1.82. Can you see why we did some of those problems off the first section? Because it's used to different areas, right? So now, find the solution. Okay, the area between the 2 z values is this, and they give us an answer. Well, that doesn't help me a whole lot here, so I'm going to kind of throw it out. If we look at those 2 z values, 1.58 and 1.82. 1.58, here's 0. 1.58 is going to be right here. 1.82 is going to be right here. We're looking for the area between it, right? So if I go on my chart here, and I go on my chart, what's 1.58? 0.4429. Did I say that right? That area. No, don't count that. They do it differently. Just look at our chart is 0.4429. They got 9929 by adding 0.5. Okay. So if I got 0.4429, correct? Now if I looked at 1.82 in my chart, what is it?
4656.
4656. Okay. That area represents. I'm going to draw it this way. All the ways out to here. Correct? So if I took the bigger area, right here, that's this whole thing, right? And I subtract that purple area, am I going to get the area between the two? So I'm going to get 4656 minus 0.4429. So I'm going to get 0.0227. So what is the chance
What the values are between them. 2.2%, or not between them, is 25, I should say. Is 2.27.
Now, coming down to it, like I said, this chapter, it's really not a hard chapter. We're using the same formulas. But again, I'm going to keep stressing this. The hardest thing is understand which formula you're going to use. Is this a binomial distribution? Okay? So today we talked about the central limit theorem. We talked about the first type of formula, which was this is z-score. Then we went into the sampling error correction, which means that we're looking for means.
So when you use the corrections,
When you use the corrections,
yeah, like when you
so you have your first one, you don't use any correction if you're just doing a regular value. Okay, if I'm looking for what's the chance it's going to happen, and I'm given the mean, given the standard deviation, and what's the chance that it's going to happen at 26. That's the normal form. Okay, now if I said, okay, here's the mean of the sample mean, what is the probability of mean happening, okay, and doesn't give us a total population it worked with, then we're just going to use that sampling area, the sigma over square root of n. Then there's the possibility of the last one, not the last one, but this one before this is if I had a sample of 500 and I'm taking a sample of 30 from that 500, what's the probability that mean is going to happen? Okay, then I have to use that better correction factor, right? And then it came to this problem. And this problem is a little different. It says that 6% of people do this, and then 94% don't. It's a sampling. It's a yes or no question, right? Didn't give you a mean. Didn't give you a standard deviation. You had to calculate it, right? Then we're going to do this binomial correction over here with the values. Okay, and you have to practice some of those binomial corrections because those do get a little more tricky as you go through. So we have another problem here. If you look at this very easily, you can tell of the members of a bowling league. I'm not going to go through it because the bell's going to ring here in a little bit. The members of a bowling league, 10% are whittled. If 200 bowling league members are selected at random, find the probability that 10 or more will be whittled. Okay, think about that problem. If members of a bowling league, 10% are whittled. If 200 bowling league members are selected at random, find the probability that 10 or more will be whittled. Why would it be 10% be whittled? No. Who bowls nowadays? Old people. Both bowling leagues are so. You might never know. You might be whittled soon. So no, but you go through here. You look about it. You look at it. You know, follow the rules. How we know it's you're either whittled or you're not. It's a binomial. You set it up. Now in this one it says find the probability that 10 or more will be whittled. You're going to subtract 0.5. So you're really, when you're writing this probability out, you're going to write it like this. You're going to write it like the probability of x being greater than or equal to, or greater than 9. Greater than 9.5. Because we want 10 or more. Okay? Because we want to include that 10. Okay? Now if this problem says, what's the probability that more than 10 will be whittled? Then this changes. More than 10, then it would be written as the probability that x is greater than 10.5. We're not including the 10. Does that make sense? So it changes how you write that, what you're looking for. The wording. You have to get into the wording part of these questions. Okay? Like I said, I'm running out of time here, and that finished off the problems. But
What happens if it's greater than or equal to 10?
that's the first case we did. That was 10 or more means greater than or equal to 10. Okay? Then you subtract that 0.5.
You have to subtract that.
Yeah, 0.5. Okay, so I think I put both assignments on Shobi, so you should know what to have to do. That finishes off the chapter. I'm guessing you're going to come tomorrow with questions. Some of these problems will be hard. Hardest part of this test, and just for reference, when you get to the test, I do not just go and say, okay, this is the order of the questions we did in the book, this is the order I'm going to put the questions. Okay, so these are going to be mixed together. Some might be the central limit theorem to start with, some might be binomial, and then you jump over to the other one, and so on down the line. So it's not going to be any particular order at all. So you kind of have to know your rules as you go through. And I'm